Learning Outcome 2, Functions and Algebra, 12.2.7. A. Investigate and use instantaneous rate of change of a variable when interpreting models of situations, demonstrating an intuitive understanding of the limit concept in the context of approximating the rate of change or gradient of a function at a point. Establishing derivatives of the following functions from first principles. F of x equals b, f of x equals x, f of x equals x squared, f of x equals x cubed, f of x equals 1 over x, and then generalize to the derivative of f of x equals x to the power n. C. Determine the equations of the tangents to graphs. Welcome back to our series of lessons on calculus. At the end of our previous lesson, we were starting to see a pattern emerge in our exploration of the gradient of a tangent to a point on a graph by means of increasingly better approximation. I also asked you to do some work in preparation for today's lesson. I'm not going to go over everything that we have done in the previous lessons now, but I do want to remind you of more general description of our mathematical problem, which we have devised, and to tell you where we are in solving the problem. Our first objective was to find the coordinates of the turning point of a graph. We realized that we will know that when we know where the gradient of the tangent to a graph is 0. And so we developed the more general problem, namely to find the gradient of the tangent to a graph at any point on the graph. A challenge that is so big that mathematicians had to invent a new mathematics to solve the problem, and that new mathematics, they called it calculus. More accurately, differential calculus. By the end of this lesson, you will be able to predict the gradient of the tangent at any point on the function of at least the following functions: y equals x squared and y equals x cubed. MacGyver will be helping us for this lesson. Hi MacGyver.
Hi there everyone.
At the end of the previous lesson, we had done a lot of hard work in exploring increasingly better approximations of the gradient of the tangent to the graph y equals x squared at the point 1, 1. What we did was to say that we wanted to know the gradient of the tangent to the function y equals x squared at the point 1, 1. In other words, the pink line. We quickly realized that this wasn't possible, so we decided to approximate it by the gradient of a line between point 1, 1 and the point on the graph where x equals 0. In other words, the gradient of the green line in this picture. And we found that the line had a gradient of 1. But as you can see, although it is an approximation to gradient of the tangent line, it is not a very good approximation. To improve our approximation, we decided to find the gradient of a line between the point 1, 1 and the point on the graph where x equals a half. In other words, the gradient of the green line. We found that this line had a gradient of 1.5. This was an improvement of our approximation to gradient of the tangent line, but it's still not good. So to improve our approximation once more, we decided to find the gradient of a line between the point 1, 1 and the point on the graph where x equals 3/4, which is the gradient of the green line in this picture. We found that the line had a gradient of 1 3/4. And although this was again a much better approximation than the previous answer we got, we could still improve on it by moving the other point closer to 1, 1. Instead of doing that though, we moved points on the other side of 1, 1 and started again. The first point we chose was the point on the graph with an x value of 2. And we found that the line had a gradient of 3. Once again, although this is an approximation, it was a poor one. So once again, we decided to improve our approximation by moving the other point closer to the tangent. We decided to find the gradient of a line between the point 1, 1 and the point on the graph where x equals 1.5.
The gradient of the green line in this picture, we found that the line had a gradient of 2.5.
And although it is an improved approximation to the gradient of the tangent line, it is not a very good one.
So once again, we needed to improve our approximation further. We decided to find the gradient of a line between the point 1, 1, and the point on the graph where x equals 1.25, and found that the line had a gradient of 2.25. Then we summarized those approximations to the gradient on the table, and this is what we got. What I noticed is that the 2 points get closer and closer to each other, both from the left and from the right. So the approximation of the gradient seems to get closer to 2.
But we needed to be absolutely sure, which meant we needed to check more values. To make our lives a bit easier, we set up a computer spreadsheet to do all this work for us. Let's have a look at it. This table looks just like the one we developed. Here in the heading, we see that the table is for the function fx equals x squared, the one we are busy with now. In this yellow cell is the x value of the point at which we are trying to determine the gradient of the tangent, in our case 1. Down the left here, we have the x values of the other point on the left of our point of interest. Do you notice how close these points get to 1 without actually being equal to 1? In this column here, we have the x values of the other point on the right of our point of interest. Again, notice how close these points get to 1 without actually being equal to 1. Finally, in these blue cells, we have the values of the gradients between our point of interest and the other point, the approximation of the gradient of the tangent line. We will try to imagine what will happen to that approximate gradient as we let the 2 points get as close together as we like. And this will suggest to us what the gradient of the tangent line is. We are now ready to use the computer to help us. I have this table here that I plan to fill in as we approximate the gradient of the tangent to the function for different values of x. It is going to help us to find good approximations to the gradient at any point on the function fx equals x squared. All we have to do is change the number in the yellow cell. Let me start by filling in what we get when x equals 1. The approximation suggests the gradient of the tangent at the point 1, 1 will be 2. Why don't I change the values of x and you record what we find?
Okay.
Right there, we change the 1 to 2, and what do we get?
It looks like the closer the x value of the other point is to 2, the closer the predicted gradient is to 4. Look, from the left, it gets closer to 4, but is less than 4, and from the right, it gets closer to 4, but it is more than 4. Let me record that.
Now, let me change x from 2 to 3 and see what we get.
It looks like the closer the x value of the other point is to 3, the closer the predicted gradient is to 6. Look, from the left it gets closer to 6, but is less than 6, and from the right it gets closer to 6, but is more than 6. Let me record that as well.
In the same way, we can use the computer to help us determine the gradient of the tangents to the graph at any point on the graph. Magava has been doing that. Let us see what his table looks like.
This is pretty interesting. It looks like I don't need the computer anymore. Look at the table. For every value of x that we found the gradient for, the gradient seems to be 2 times the x value. I'm going to write here.
You really have done a great job.
Thank you. I'm enjoying this.
That's great because we haven't finished yet.
I had a feeling you were going to say that.
I'd like you to repeat all of that for the function y equals x cubed.
Okay, but I'm going to work smart, not hard. I'm going to go straight to the computer.
And while you do that, I'm going to do some algebra with the learners watching. As much as what we have done has been useful in helping us to develop a deep understanding of what it is that we're doing, there comes a point where we need to try and be even more efficient. And that is one place where algebra can really help us. Rather than working with actual numbers, let me work here in general terms. We're going to carry on working with the specific function f(x) equals x squared. To start with, let me choose a point at which I would like to approximate the gradient. Let's choose this one here. Now, if that point has an x-coordinate of x, then its y-coordinate will be fx. So I'll call the point x fx. In the approach that we have used, we have always chosen another point. Let me choose that point to be over here. What I plan to do is to determine the gradient of this line. To determine the gradient, I want to calculate the vertical change and the horizontal change. As a convention in calculus, we refer to this horizontal change as h. If the horizontal change is h, then the x-coordinate of this point will be x plus h, f of x plus h. The vertical change is then f of x plus h minus f of x, which gives me the gradient, which is equal to f of x plus h minus f of x divided by h. What I've just written there is a very important relationship in calculus. We will see it a lot in the future. Now let's think about what we have found in relation to the function we've been dealing with, the function f of x equals x squared. Since f of x equals x squared, the top line of this gradient becomes x plus h squared minus x squared. When I expand that bracket, I get x squared plus 2xh plus h squared. I must still subtract x squared. All of that over h. Now I can simplify the top line and I get 2xh plus h squared over h. When I take out the common factor of h in the top line, I get h times 2x plus h, all divided by h. And simplifying one more time, I get that the approximate gradient is equal to 2x plus h. And that is exactly what we found with the computer spreadsheet. Remember, MacGyver said, it appeared as if the approximate gradient of the tangent got closer and closer to 2 times the x value as the distance between the point of interest and other randomly chosen points got smaller. And with our algebra, we see that as we bring the 2 points closer together, h gets closer and closer to 0, and so the gradient gets closer and closer to 2x. I really love it when algebra confirms what we have found. Now let's go and see how MacGyver is doing with that function, f of x equals x cubed. MacGyver, how are you doing so far?
Not too badly, but this is taking time.
Are you seeing a pattern yet?
Nearly, but I could well do with another few minutes.
Very well. I'll do the algebra of that function with a viewer so long. I have set up the gradient relationship in exactly the same way that I did for the function f of x equals x squared. See, here's the point x, f of x, again, I have called the horizontal change h, which makes the other point x plus h, f of x plus h. Once again, the gradient becomes f of x plus h minus f of x divided by h. This time, f of x is x cubed. So the top line of this gradient becomes x plus h cubed minus x cubed. When I expand the bracket, I get x cubed plus 3x squared h plus 3x h squared plus h cubed. I must still subtract x cubed. All of that over h. Now I can simplify the top line and I get 3x squared h plus 3x h squared plus h cubed over h. When I take out the common factor of h in the top line, I get h times 3x squared plus 3xh plus h squared, all divided by h. And simplifying one more time, I get that the approximate gradient is equal to 3x squared plus 3xh plus h squared. That is not as pretty as the last time, but I think we can still work with it. Let's look at this expression again. 3x squared plus 3xh plus h squared, as we make h very small. H squared will be very, very small, and 3xh will also get pretty small. But as h gets very small, 3x squared stays unchanged. So it would seem as if we can make this expression as close to 3x squared as we want simply by making h small enough. I wonder how that compares to what MacGyver has found. How far are you, MacGyver?
I'm finished.
Okay, let's compare what you found to what we have found. If our algebra is correct, we are predicting that you will have found that the gradient of the tangent at each value of x will be very close to 3x squared. Is that what you get?
Let me have a look at my table. I found that when x is 2, then the gradient will be 12. And your formula says that it should be 3 times x squared. Well, 2 squared is 4, and 3 times 4 is 12. So that is the same as what I found.
Please check, say, -2.
Okay, I found that when x is -2, then the approximate gradient will also be 12. And your formula says that it should be 3 times x squared. Well, -2 squared is 4, and 3 times 4 is 12. So that is the same as I found. Pretty impressive.
Yes, it is. I think that you have enough to think about for one lesson. Let's quickly go over what we have done today. After a good deal of investigation, some manually and some with a computer spreadsheet, we found by taking points closer and closer to a point on the graphs of two curves, f of x equals x squared and f of x equals x cubed, that we could predict the gradient of the tangent at any point on the curve. In the case of the parabola, f of x equals x squared, the gradient at any point, x, f of x, is 2x, and the gradient at any point, f of x equals x cubed, is 3 times x squared. And now your task for this lesson. Using the formula, gradient equals f of x plus h minus f of x, all divided by h, to determine the gradient in terms of x and h of the line joining any 2 points on the functions f of x equals x squared and f of x equals x cubed, as I did in the lesson. Then try the functions f of x equals x, f of x equals 1, and f of x equals x squared plus x. Well, that's all for today. Good luck with your task.